Welcome back to the deep dive. We're here again to sift through the research and pull out the key insights for you.
That's the plan.
Today we're diving into machine learning, specifically generative models. There's this recent paper looking at a fundamental link between two different families of these models.
Right. You've got Gaussian diffusion models on one side. These are, well, they've become really dominant for continuous data, the images, audio, that kind of thing.
High fidelity stuff, and then the other type.
Discrete diffusion models. These are built for data that comes in distinct pieces, like words in text, or maybe nodes in a graph, or even molecules.
Okay, so different tools for different jobs.
Yeah.
But the paper suggests there's been a bit of an imbalance.
Yeah, you could say that. The Gaussian diffusion world is very well developed. People have figured out all sorts of advanced stuff, efficient ways to set up the models, faster training, really quick sampling methods, even distillation to get generation down to like a single step sometimes.
Right, a mature toolbox.
Exactly. Whereas the discrete side, the paper calls its design space primitive in comparison.
Primitive. Ouch.
Well, maybe a bit harsh, but the point is they often use simpler approaches. Things like mean parameterization for the part that cleans up the noise, and often rely on this slower, step-by-step ancestral sampling to generate anything.
Okay. And within that discrete world, the paper focuses on two specific kinds.
Yes, uniform state diffusion models, USDMs, and masked discrete diffusion models, or MDMs.
USDMs and MDMs, what's the core difference there? I think that the paper had a figure on this.
Yeah, figure 5 helps. It's about how they add noise, the forward process. In a USDM, think of a word token. As noise gets added over time, that token could change into basically any other word in the vocabulary.
So it can jump anywhere.
Right. But in an MDM, it's different. A token either stays as it is, or it flips to a special mask token.
A placeholder, sort of?
Kind of. And the crucial part is, once it becomes mask, it's stuck like that. It can't change back or become a different word during the rest of the noise process.
Ah, okay. So that noise process difference must affect how they generate things in reverse, right? When they remove the noise.
Absolutely. Because USDMs allow these free jumps between states, they have this built-in ability to, well, correct themselves during generation. If the model kind of guesses wrong about a word early on, it has chances later in the process to revise that guess.
Self-correction, that sounds useful.
It is, potentially.
Mm.
MDMs don't really have that. Once they decide what word goes into a masked spot, that decision is final. It's unmasked and locked in.
Which might explain why they sometimes need extra steps, like those predictor corrector things.
Yeah, that's often needed to refine the output for MDMs, which adds to the computational load.
But here's the twist, right?
Yeah.
Despite that self-correction feature, the paper mentions USDMs haven't actually performed as well as MDMs historically.
That's been the case, which makes the central discovery of this paper really interesting.
Okay, let's get to it. What did they find?
They discovered that these uniform state discrete processes aren't totally separate. They're actually an emergent phenomenon of an underlying continuous Gaussian diffusion process.
Whoa, okay, emergent. So the discrete behavior just kind of pops out of the continuous one. How does that work? What connects them?
The bridge, according to the paper, is the argmax operator.
Argmax, like select the maximum.
Exactly. Imagine the underlying Gaussian process is dealing with continuous scores or probabilities for every possible word at each position. The argmax operation just looks at all those continuous scores and picks the single word with the highest score. That's the step that takes you from the continuous fuzzy probabilities to a definite single discrete word. Figure 1 of the paper gives a nice visual for this.
Okay, I think I get it. The continuous model proposes probabilities, argmax makes the final choice. That's the link. What's the big deal about finding this link, this diffusion duality?
The really big implication is practical. Because of this theoretical connection, you can now potentially take all those sophisticated techniques developed over years for Gaussian models.
The faster training, the better samplers.
Right, all of that, and transfer them directly to the discrete models, especially these USDMs. It basically unlocks a much richer set of tools for designing and improving discrete generative models.
So it's not just a conceptual link, it's a practical bridge for methods. Does it also connect the math behind the diffusion itself, the parameters?
Yes, it does. The paper shows that the argmax transformation implies a specific transformation of the diffusion parameters, things like the noise schedule. They define this diffusion transformation operator that mathematically links the parameters in the continuous domain to the equivalent ones in the discrete domain.
Okay, so the math lines up.
It provides the concrete way to map techniques across.
Now, the paper also says that even though they're linked, they're still treated as separate Markov chains. And they have different ways to measure performance, like different variational bounds.
They do. They result in different mathematical expressions for the evidence lower bound, or ELBO. This is basically what the model tries to maximize during training, how well it explains the data.
And is one better than the other?
Well, that's another key finding, Theorem 3.1 in the paper. It shows that the ELBO derived directly from the uniform state discrete diffusion process is actually tighter than the ELBO you get from the underlying Gaussian diffusion process it's linked to.
Tighter? What does that mean practically?
A tighter bound is generally better. It means the objective function you're optimizing during training is closer to the true likelihood of the data. So optimizing the discrete ELBO might lead to better model fitting compared to just optimizing the bound from the underlying less direct Gaussian perspective. It gives a strong theoretical reason why working directly with the discrete formulation, now enhanced by the duality, is a good idea.
Okay, so we have this duality. Argmax is the bridge. It connects the parameters via that T operator, and the discrete ELBO is tighter. How do they actually use this to make discrete models better in practice?
Right. They developed a framework based on this duality, which they call DUO. And they use DUO to tackle two main problems: making training faster and making sampling faster.
Let's start with training. How does the duality help speed things up?
They used a curriculum learning approach. The basic idea is to start the training in a way that's closer to the simply underlying Gaussian process, and then gradually shift towards the more complex discrete process.
How do they do that?
They rewrite the discrete training objective, the negative ELBO, using those underlying Gaussian latent variables. Then, instead of using the hard argmax right away, they use a smoothed-out version.
Smoothed out?
Yeah, using something called tempered softmax. It has a temperature parameter, let's call it. When CUT is high, the softmax is very smooth. Its output looks a lot like the continuous probabilities from the Gaussian view. This makes the initial training objective behave more like the Gaussian one, which is often easier to optimize.
And then they lower the temperature over time.
Precisely. They anneal down towards zero. As it gets smaller, the tempered softmax acts more and more like the true argmax, becoming sharper. So the training gradually transitions from mimicking the simpler Gaussian objective to optimizing the actual discrete objective.
Clever. Like training wheels that gradually come off. Did it work? What were the results?
Yeah, the results were pretty significant. They found this duo framework with the curriculum learning accelerated the training convergence by at least 2 times compared to earlier USDM approaches like UDLM.
Twice as fast.
At least. They showed duo getting better results, like lower perplexity on language tasks, after about 500,000 training steps than the old method got after a full 1,000,000 steps.
Wow, okay. That's a solid speed up. Did it help with stability too? Training these models can be tricky sometimes.
Definitely. They reported much lower training variance. They even measured the variance of the gradients for specific parts of the model and found it was reduced by an order of magnitude in some cases. Much smoother sailing during training. You can see graphs of this in Figure 7 and numbers in Table 3.
So faster and more stable, did the final models end up being better as well?
Yes, the improved training seemed to translate to better final performance. Duo achieved lower perplexity, which means the model is better at predicting the text compared to previous USDMs and even some Gaussian diffusion models on standard benchmarks like LM1B and 1Wikitext.
Can you give a specific number?
Sure, on LM1B, Duo hit a perplexity of 33.7, whereas the previous UDLM was at 36.7. That's a noticeable improvement. Table 1 has the comparisons.
And how did it compare to other kinds of language models, not just diffusion ones?
They showed competitive results, even beating standard autoregressive models on some zero-shot generation tasks, according to Table 2. Yeah. They also did an ablation study trying to isolate what caused the improvement.
Oh yeah, what did that show?
It suggested that the improved loss formulation itself and the curriculum learning strategy contributed roughly equally to the gains. It wasn't just one thing. They also looked into that temperature parameter and found a sweet spot, around 0.001, that balanced bias and variance well. Figure 8 discusses that trade-off.
Okay, so the duality delivers faster, more stable training, leading to better USDMs. That's a big win. What about the other side, generating samples from a trained model? Did the duality help speed that up too?
Yes, and this might be even more dramatic. They used the Duo framework to adapt techniques originally designed for fast sampling in Gaussian models, specifically consistency distillation.
Consistency distillation. I've heard of that for images. The goal is to get good results in very few steps, right?
Exactly. It builds on ideas like probability flow at ease, deterministic samplers. The aim is to train a separate consistency model that can jump directly to good samples from noise, bypassing many intermediate steps of a pre-trained diffusion model. They created a discrete version using Duo, calling it DCD, Discrete Consistency Distillation.
And how much faster did DCD make the sampling for these USDMs?
Orders of magnitude faster.
Yeah.
They showed they could reduce the number of steps needed, the number of function evaluations, or NFEs, from something like 1024, which is typical for ancestral sampling, down to just 8 steps.
8. From over 1,000. That's huge. Without sacrificing quality.
With minimal impact on sample quality, according to their results in Section 5.2. It's a massive speed up.
How does that compare to trying to speed up the masked models, the MDMs?
They showed that their distilled USDM using DCD performed better than distilled MDMs, especially when using very few sampling steps. Figures 3 and 12 illustrate this comparison.
And does that self-correction ability of USDMs play a role here?
That seems to be the key insight. Because USDMs can revisit and change tokens during generation, they handle the aggressive reduction in steps much better. If an early step makes a slight error, later steps, even if there are only a few, have a chance to fix it.
Whereas the MDMs, once they unmask a token, it's fixed. So errors made early in a super fast generation process might just stick.
That's the idea. That lack of self-correction seems to hurt MDMs more in the very low NFE regime. The USDMs are inherently more robust to this kind of few-step generation.
Did they explore any other fast sampling tricks?
They also mentioned using a greedy tail sampler. That also got the steps down to around 8, and seemed to maintain or slightly improve some metrics like generative perplexity and entropy compared to the standard slow sampling. Figure 4 shows that.
Interesting. And they hinted that maybe the distilled MDMs, while sometimes matching on metrics like perplexity, might produce less diverse outputs. Something about lower entropy.
Yeah, there was a suggestion of that in figures 3 and 11. Achieving high diversity in few-step generation is always a challenge, and maybe the USDM's ability to explore and correct gives it an edge there too.
Okay, so let's try to wrap this up. The core achievement here seems to be establishing this really fundamental link, the diffusion duality, between continuous Gaussian models and these uniform state discrete models.
Right. Centered around that argmax operation.
And crucially, they didn't just leave it as a theoretical insight. They built the Duo framework to actually use this duality.
And demonstrated really significant practical benefits, making USDM training twice as fast and more stable and slashing sampling time by, well, a couple orders of magnitude.
Which really changes the game for these uniform state models. It makes them much more practical and competitive, particularly if you need very fast generation, where they seem to now outperform the masked discrete models.
Absolutely. It revitalizes that class of models.
So a final thought for our listeners, based just on what we've discussed from the paper, it feels like this discovery potentially opens a door, doesn't it?
It certainly seems that way. If this duality holds and allows technique transfer, then that whole rich, mature toolbox developed for Gaussian diffusion, maybe large parts of it could now be adapted and applied to further improve all sorts of discrete generative models in the future. There could be a lot more innovation coming down this path.